Hey everybody, good to see you here, Snare. We have HCT and we have 320. Let's do this. Let's hop over to the assignment. There are questions on number 2. Let's go over, do some 320. Here we are on the main page. We were doing some 320 earlier today. Check out today's earlier video where we did some of the questions and we talked about the theory behind it. So task number 2. Task number 2 says, choose 2 x variables to create a model predicting demand. Create the simple linear models first and then find transformations for each of them using choose order. And I added this in right here. I would use choose orders. Like, note the preferred method for finding transformations of the x is choose order. We're not transforming both of them. Once we use choose order for the transformations, how do we determine which order to transform, or how do we transform? Great question. And I think we should have it in the notes for this week. If not, I'll go through some examples of it. So let's make a model right here using one of the x's and talk about how to use the choose order. So when you make a model right here, we're going to go demand tilde avg temp comma data equals MOS sample. And there we go right here. That's just a graphical error. And let's go down here to choose order. People are allowed to use the find transformation. Let's go look at this. So at this point especially, I want us to think about because we're going to learn about this topic here coming up. When we look at the choose order output, and I'll vanish from the screen. I changed notes as my guy for the code, but I just want to make sure I did it correctly. Awesome. For chapter 12, can we do the traffic checks on a certain section of highway? You bet. We'll do that next year, Clarissa. You got it. No, definitely. Like we review, we practice. You got it. So when you look at this code right here, what maybe jumps out as not so good of a model, Snare? What maybe jumps out as not so good of a model? Like, take a look at the output right here, and remember that higher R-squared adjusted is better. So what maybe jumps out as not that great of a model? So I would probably use a certain transformation right here. So what maybe jumps out as not that great of a model? What maybe jumps out as not that great of a model? You can use the find transformations or the choose order. We're fine either way. But maybe there's some more of a what fit this. Order 1 has the lowest R-squared adjusted. Exactly. That should jump out immediately. We should be like, ooh, that's not that great. But the polynomial model, the second order, is almost one of the best. Like, these are the best right here. This is the best. That's the second best. This is the third best. And actually, if we go by Akaike's information criteria, this one is the best right here. And so that'd be a clear choice by Akaike's information criteria. Amazing Japanese statistician. One, like I mentioned, in Japan, because he's in their academy of like top tier scientists. Like he is like one of the top statisticians in the world, and his country was like, you are awesome. And so he changed the world with this right here. So he created this measure of closeness to the truth. The lower it is, the better it is. The lowest it can go is negative infinity, and we'll talk more about that throughout class. So his measure of closeness to the truth that a model would suggest that we should use this one. And by adjusted R-squared, like you could say this one, but I'm going to go right here. So there's a lot of ways to look at stuff. So we'd use lowest AIC is better, and an AIC within 2 is virtually identical. So you would look at these and be like, okay, this is the lowest. And here's kind of what you would do also. When you look at this, you want to say, does this actually help? So look at all these upper degree polynomial models. Mainly, it looks like the data just has like multiple bends, or just one bend through the data. What do you think? Do you think this data has like 6 bends or 5 bends? Because if it's a 6-degree polynomial, to have 5 like inflection points on it. I don't know the mathematical terms anymore. But do you think how many bends do you think this should have? Or what do you think is a decent enough form for this data? It looks more like a kind of, if you think about it, like what does it kind of look like right there? Which I think we could go with this. And I'll show a few ways to do this. Right now, we're just mainly we're mainly trying to just make multiple models and examine multiple models and think about how these work. So what do you think we should use right here? Like, second, do you think we should put like a 10th degree polynomial? Because you can do some craziness with this. So it looks like it does look like a Twizzler. All those lines are pretty close. I do agree with that, HGT. They do look pretty close. If you go, it's max order, I think. Max order equals 15. So you can do some craziness right here and get something like this. Now that looks like crazy party Twizzlers right there. And we're still seeing the lowest Akaike information criteria on the second one. So looking at this right here, and this is absolutely ridiculous. Ridiculous? Most of them kind of look like deformed parabolas. Exactly. Snare, you're exactly right. I mean, if you look at this, look at like the whole stream of it. It just looks like it's creating a parabola, right? Like if you were to go through the center of this, and the parabola is just the second order polynomial. So yeah, and I'll show you a few ways that are acceptable. Here are the acceptable ways to do this one. When creating this, the best way of doing it is going to be to do the following, which is going to go a little bit advanced. So, because I say next transform the x variables, create a multiple with the transformed. So I'm just going to, you need to include both of these transformed. Let me put here, Brian is just showing how to transform one variable. I'm not making a multiple model. Brian is not making... I try not to do exactly what you're doing, but I'm going to show how to transform one of these variables. Yes. So you won't exactly have to store it. What you have right here, Snea, exactly is the poly function on it. And watch this. If we go over here and just drop the poly in right there, that function you did right here, this is the variable. We don't actually have to include that anymore because it's already in the data set. So you ran the poly function. Let me zoom in on it so we can see a little bit better. You're running the poly function inside of here on the variable average temp, taking the second degree polynomial of it. And so you won't actually have to transform it there. It can be used in the model and used a higher order polynomial, which is kind of transforming it. I just stored it to make the code more organized. It might work that way. You know what? Let me try this. I've never tried it this way. There's so many ways to do things. Let's see if this gives the same output. I'm gonna throw some you know what I'm gonna do? Oh my gosh. I'm throwing 100 points. I don't care. Amazing work. I think what's really awesome right here is you're kind of figuring out how to do things. I'm not just telling you how to do them. So you're like, hey, if I do this right here, I can store this, make it more organized. I can have the X. Now, I wouldn't really call it, I think you called it something better. You called it like this. We could say like AVG temp poly. So maybe we'll call it this right here. And let's put this right here. And then we can see here's the first degree polynomial, which is the linear relationship. And here's the second degree. Does that make sense right there? Like, I think it was easier to make the multiple model when I stored both variables. Exactly. And then you could also do the other variable and you just have to do plus right here. So I'm also fine if you transform by doing let's do a different thing right here. If you were to take your variable, I just want to see what people do because so let's go here, average temp squared, and someone could just take, I would not suggest this way, not the end of the world if you do this, and you would need to store it. Is it grabbing? Oh, it's looking at the global environment. So if it can't find it, what's it mad about? Unexpected, oh, because I got the plus. There we go. 32%. Yeah, so that's just doing the polynomial. 32%, 42%. I mean, if you look at this right here, so here, just look at this alone right here. I just went off the notes and so I used poly. Exactly. The notes have the poly, so the notes will always have the suggestions. I would do it this way, but you could transform it by doing, like, as you can tell, this is not as good. Look at this right here. 41.5 R squared adjusted, and look over here, 31. I mean, the R squared adjusted is about 10% lower, which is a big dip. Then look right here, 1407, and yeah, good. This is the worst model, 1519. So this model right here has a better, and this is what you'll be doing later on, this model has a better typical miss, has a better R squared adjusted, and like, if you compare these two, does this make sense right here that comparing these two models, this model here with both terms, which is actually a multiple model right now, does better than the non-multiple model? Does that make sense right here? This model that has both terms and is a multiple model, this one just has the squared term in it. This one has the both terms, the simple linear term and the polynomial term, is doing much better via the RMSE, which is the typical miss the model makes when predicting demand, and the R squared adjusted, which is R squared adjusted for how many variables are in the model. Looking down here at the other one, this is about 100 higher. Yep, exactly. And then you saw during morning office hours where I did these comparisons and made the table. So you hopefully, and check out morning's office hours if you want to know how to make this. I mean, I'm basically showing the code again, where I ran and made a table right here, which I think we still have it all stored. And I kind of made up some fake data right here where I was taking those numbers. So you can see I have the RMSE, the R-squared adjusted, and kind of conditions. So great job right there. Yep. And how are you finding this assignment? It sounds like you're pretty far into it. And hopefully as we go through class this week, you'll be like, oh yeah, that makes sense. We did that. But assignment going pretty well. And then we're going to do a 201 question here. But hopefully this assignment's being like, yeah, it's making sense. I'm getting I get what we're doing. Like we're just making some models. We're just predicting things. We predict data. We try to explain data and we try to make better models. And the better our model is, the better we can predict some phenomenon in the world. And just loading up some data here as we go. I think the coding's a little more challenging, but it's good. Yeah, it may be a little bump in the coding right here, but always feel free to ask. Anytime you're stuck, I think people know that. Anytime you are stuck, let me know what you're stuck on and be like, Brian, I don't understand what's going on with the coding. My coding's not working. Of course, for take-homes, you can't do that. So always ask all the questions before the take-home. And the more questions you ask for the take-home, the better you will be. For task 4, would it make sense to compare the overall p-value of the model as well, or would RMSE and R-squared adjusted be the best? Really great question right there. Thank you so much. Let's show some 20 points to the chat also. It's probably most important that your overall p-value for the model is what? So whenever you're looking at the overall p-value for the model, which most of the time we're going to see, what would you expect or want your overall p-value for the model to be for every single one of them? We're probably not going to look at this so in depth. I guess we could look at the F statistic. Might not be so bad to look at. Yeah, and oh, that's interesting. Ooh, I guess because it's different F distributions. So I don't know what the p-value is going to be because those are different F distributions. Below 0.05 exactly. So both of these models are statistically significant. All the terms in these models are statistically significant. I guess it would be QF. Let me think here. PF, I think. And yeah, there it is. So degree of freedom 1, degree of freedom 2. So, okay, good. And yeah, that's the p-value right there on it. And so if I increase this, it should get smaller. No. Oh, that's the area before it. So we want to do 1 minus that. It's just going to turn out to be like 0. Oh, no, it's doing it. Good. Okay, so I can get the p-value better estimated via this. I might just go to that. This one has an F statistic of this with degrees of freedom 1. Because it's just got one term in the model outside of the intercept. And wait. Oh, wait. There's the 2 degree of freedom 1 numerator and denominator degrees of freedom. This is definitely not needed. Yeah, it's saying 0. Options digits 99 between 22. Options SciPen 99. Oh, yeah. The p-values are basically 0. Even R at this point is not. I wonder if Wolfram Alpha would give us it, but the p-value is so small here for both of these models. Like at some point, it's just going to calculate them as close as it can to 0. So we can see it approaching 0 here. I turned the SciPen so I can get a bunch of digits, but at some point, it's basically approximating 0. And yeah, so at some point it just breaks off right there, and it's like, yeah, your p-value is so tiny that it's just going to call it 0. Oh yeah, ask another question. Feel free to. But this is me actually estimating the p-value, and I wish it would go even smaller, because I mean, if I want to know what the p-value is, that's weird how it. Ooh, now it gave the. Oh, I typed the same number. That's why I gave the same. That's so weird that it's actually having. That's so weird. So could we mathematically figure it out? No, it didn't have every time. It halved. That's weird. Bunch of interesting stuff about data. But after this point, it won't show me. It'll just round it to 0, which is a bummer. I don't know why. Might have to do with like double decimal precision and number storage and memories. But I mean, I would think it could figure that out. When I transform my second x variable, my lowest ASC in order 1, is that okay? Or does it have to be a polynomial? What you'd want to do, you could try the fine transformation on it then. You might try your fine transformation function, which we don't really have a... it's mad at me. I'm using a variable I shouldn't use right now anyways for it either. So this is saying my x should be raised to this power. Of course, it is with a y raised to another power to create this relationship. And you see, it does actually help out, it looks like. The non-transformed is 32. The transformed is this. So you could try it with fine transformations. We're destroying the interpretation a little bit here, especially with fine transformations. We're also supposed to transform the y, technically speaking. It'd be interesting to see what happens. I mean, we're just making a few models here to compare them. This is not groundbreaking research. The whole point of this assignment is to be able to compare multiple models. So you're basically going on this track of making different models. So I am okay with however you choose to transform it. The graders should be nice on it as long as you've found a transformation, or if you could say, like, I don't think I should be transforming this. I just used the second order instead because it was my second lowest ASA. Yeah, you could go with that. So if you really want to be very statistical, which we should be, you could say, I would not use a transformation here because there is no good evidence to suggest that a transformation would be a better model. But for virtue of creating a transformed variable, I'm going to use this polynomial term right here, the second order polynomial. So I think that's fair to do, statistically speaking, we would not choose a transformation at this point or a polynomial degree to raise the variable to. But with doing an assignment, I shall humor this and use the second order. Does that make sense right there, Snap? The whole point is to look at multiple models and then talk about which ones are better and worse. And probably that's going to lead you to not like those models as much. Like as you look through the models are going to kind of be like, yeah, you shouldn't have done that, which is all right. That's the point. The whole point is the end of this when you look at the models and you're like, oh, which model is best? And then you have the ability to look at models and make comparisons and then look at the conditions for the model. Maybe it'll help with some sort of condition, or maybe it'll hurt some sort of condition. So we'll see as we create models here how well the models do. That's the whole point. It'll be very interesting to see what people do for this assignment because there's a few different ways to go, and that's the theme of statistics. It's all about choices, and statisticians make different choices on how to analyze data. I love it. It's like a choose your own adventure when you have enough techniques. I want to knock the coding portion out of the way so that I can start the interpretations after tomorrow's class. Yes, you will be completely on track. I think you'll do great. Awesome work. Let's see. 201. Dimitri, good to see you here. I didn't say hey to Dimitri. Clarissa asked for chapter 12. Can you do the traffic checks on a certain section of highway? You bet. So let's go back to the traffic checks on a certain section of highway. So a traffic check on a certain section of highway. Where is it at? I think right here. So traffic checks on a certain section of highway suggest that 65% of drivers are speeding there. So we would expect if you do 0.65 times 0.65, you're welcome so much there. So you said thank you. We would expect that 0.65 times 0.65 equals this, mathematically speaking. But we do have a condition right here. And what condition do we have? So I'm pulling up some notes right here to help out. If you're watching this, I've got some really important notes for this where we do the rules of probability. So the rules of probability right here follows. Rule 1, probabilities between 0 and 1. Rule number 2, all probabilities add up to 1, the set of all probabilities. Rule number 3, the complement rule, that probabilities, if you have the not of an event, like something happens or does not happen, like what's the probability it snows or does not snow. And then I did fix that typo. If you're in the online class, it is fixed, but I didn't re-upload it because then it removes it. And then rule number 4 is the addition rule, where we can add together disjoint or mutually exclusive events. And that just means that they both can't happen at the same time. Review the rules. And rule number 5 is the multiplication rule, which says we can multiply independent events. So a very, very, very important rule for this is that these are independent. And here's kind of the shorthand. Take a screenshot of this if you need it. The shorthand of the rules where multiplication is the word and, say, a car is speeding and the next car is speeding. And the rule is that they're independent. We have to meet this rule to do the multiplication. And then we have the addition rule, which is disjoint. Disjoint is the same thing as mutually exclusive. We use the word or, like this happens, or this happens, or this happens. And subtraction is disjoint because when you have things that are complements, you're saying either this or not this, and they are disjoint because they both can't happen, and you are subtracting. So this is the online class, and sometimes I look at this and I'm like, I can't believe I wrote all this. But I did, because I added Spider-Man. Everyone loves Spider-Man. So with this right here, let's take a look at the rule and see why this does not apply. So you might say, well, why can't you just multiply these cars right here? The multiplication rule might suggest that there is a approximately 42% chance that two vehicles in a row are both speeding. What's wrong with this reasoning? Well, we've got some notes on this to help out, and let's take a look at some cars on the highway. If it is 5 p.m., this might be you. You are that car. Now you're here in 5 p.m. traffic and you want to go 100 miles per hour. So you're like, gosh, I would love to go 100 miles per hour. But your speed of your car might be what on the car ahead of you? Because we're going to look to see if two cars are speeding right here, but the speed your car is going, right here, your car, might be what of the car that's ahead of you? The speed your car is going might be what of the car that's ahead of you? And this is where we break the rule. The speed your car is going on the highway, because we're looking at two cars in a row and the probability that they're both speeding, the speed your car is going might be dependent on the speed the car is ahead of you on the highway, the car ahead of you. So the probability of two cars speeding, while it makes sense to say the first car is speeding and the second car, exactly, Ella, great job. And Ella, if you have questions, feel free to ask. We're kind of at that lull already. So we would have here, so they are not independent. There we go right there. We might start doing some speed runs. I speak too quickly at times. We might start doing some speed runs of chapters. So we could do that, Ella, because I might try to take these out of the videos and do speed runs and just cut the thing and, epic speed run. I use the voice I like.
Epic speed run of statistics. Brian Stevens.
So I did the voice. I had a little bit different of a sound effect, but similar to that. Like a little, I don't know. It's fun to mess around with the sound effects on this thing. Smoke-free seating question? You bet. Of course. You're here. You get to choose what we do. So smoke-free seating section, that is chapter 13. Let me go grab that. We did these conditions earlier today. I put them on the Discord. And let's go grab the smoke-free seating question. This one is tricky because there is a way to make an error on it, and usually I just give the points back. So if you made this sort of error, please tell me. It is a tougher question. This one is tougher, and it's very easy to make a mistake on it. Here we go. Okay. So the first thing we need to do is take a screenshot of the question. And let's bring it over here. There we go. And let's think about this question. Okay. So with this question right here, we have 132 seats are being planned out. 8% is the true proportion, hint, 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 of people who want smoke-free seating. That's apparently what studies say. Apparently that's true. So what do we have right here? It kind of gives away the answer with this, and this is the answer to the question. So notation-wise, I'm going to highlight two numbers and tell me what these are in notation. We talked about today knowing the notation, knowing the formulas, and knowing these types of questions is how to solve them. So what is any of this notation? What is any of this notation on the screen? And I'm going to start to write out equations while people figure out the notation. Well, it's not 3 yet. Exactly. Great job right there. And technically 0.58, technically 0.50, but still like 58%. So you are correct. And this right here will be sample size. And this right here will be P, and it'll be equal to 0.58. So the only question, Ella, which everyone's going to ask, I know you know it, so I'm going to say it. So great job on those answers, is everyone asks, what is Q? Don't worry. If you're ever watching, you're like, what is Q? Don't worry. That's a very common question. P and Q are complements. So P and Q add up to 1. So these add up to 1. So it's just 1 minus P is Q. 1 minus Q is P. These are complements of each other. They add up to 1. Very, very, very common question to say, what is Q? You'll hear it in class. I promise. I'll be writing it, and I won't have said what Q is. And someone will say, how do we find Q? And I'll be like, it's 1 minus P. And you'll say it in class too, and we'll be like, yes, we know it. We memorized it. So we have the equation right here. And what we're going to do is we're going to go and we're going to do P times Q over n square root. P times Q over n square root. And we just found the standard deviation. So now we're going to use MuBot here. MuBot, help us out. Bring us to that David M. Lane applet MuBot. And we're going to put here in the mean and the standard deviation of the distribution. We're going to put in the mean and the standard deviation. So we're going to go and take our mean and standard deviation. The standard deviation was what we just found now. The mean is going to be 0.58. To just make this very, very clear, we literally have this is right here. Hopefully that makes sense. This is literally the mean of the distribution. And then I plugged in, just so people can see. I'm worried someone's like, how did you find that? You did it so quickly. I'm like, okay, wait, I'll slow down. I understand. I don't say that jokingly because I watch videos where people show how to make like things in Photoshop or like After Effects. So I watch these videos to like learn how to make stuff. And then they do it so quickly. And I'm like, whoa, slow down. And they're probably like, no, I'm going slow. And I'm like, no, you're not. You're doing it too quickly. I cannot learn at this pace. So I do appreciate when people say slow down, you know, because I experienced that when I watch a tutorial video and I'm like, this is way too quick. So the P times Q over N square root is the standard deviation, and the sampling mean of the distribution was that. Sometimes it doesn't show that last number. You can get it to, we don't want to do that. That's all right, it doesn't show it, but it bums me out about the David M. Lane. 0.58, good. And then we want to go 3 standard deviations up. So we don't get to see it? Why would you do that to us, David M. Lane? Why would you do that? So we've got here 3 standard deviations. Let's times it by 3. And let's add that to the mean. And Ella, does this make sense right here that I've gone up 3 standard deviations? Although we can't see it on the curve, does this make sense here that this number here, like right here on the curve, would be 0.7088? Does that make sense that this is 1, 2, 3 standard deviations up, which is what this question is seeking out? It is seeking out 3 standard deviations above the mean, exactly. So this is the what we need. It's not how many seats we need that are smoking or non-smoking or something. I think it's non-smoking. This is not how many seats we need. It's the what of seats we need. So this is not how many seats we need. This is actually this number that we found right here, which was 3 standard deviations above the mean. We just went to the mean, 0.58, went 3 standard deviations up. This number right here, which is 3 standard deviations above the mean, is the what of how many seats we need. This is the what of how many seats we need. Think about we're doing the sampling distribution of the sample proportion. So that's an answer to the question. This is the what for how many seats we need. There's 2 words to use. More commonly, we might just call it like something percent. This is the percent, exactly. More commonly, this is just the percent of smoking. Like you might say proportion. Someone might be like proportion, but like that's the percent we need. So all we're going to do is take the sample size of 132 and multiply it by that, and we get this. Now here's what you have to do. Elizabeth, good to see you here. Feel free to ask any questions. Here's what you have to do, no matter what. Like if my answer was this, here's where people make a mistake. If my answer is this, what do I put right here? So Ella, this is where people make a mistake. Now my answer was a little bit different, but let's pretend that's my answer. If my answer was this, what do I put into this field right here? So this is where it's just, I don't know. They had to do that on this question. So this is where people make a mistake. They see this, and then what should you do? Exactly. That's the mistake. Great job, Ella, right there. We should get this right, unless I made a mistake. We get it right. There we go. Very, very common error right there. I've even seen instructors make that error. I had an instructor come to me and say, Brian, this question isn't working correctly. And I said, oh, it says round up. And they're like, well, that's weird. And I'm like, yeah, I don't know. It's got to round up no matter what. No matter what. Round up no matter what. My Pearson's just being crazy. Would you mind going with the plastic arrow on a spinner for child game? Yeah, of course. Of course. Let's do that one here. Definitely. It is. Feel free to ask any questions at any time. And you asked at the perfect time, ironically, because we are right here just finishing another question. But if anyone is watching right now, remember you can ask questions at any time. I try to put them in order and try to like organize in my head the questions, and we then do it. Here we go. Perfect time to ask a question, though. Perfect time. It's always the perfect time. So what I want you to think about right here with this is let's grab this and let's talk about this. So could you go over the logic behind the histogram question? You bet. You got that one next. Perfect time. Always perfect time, right? So what we're going to do, it sounds like my mic popped. I don't like that. we're going to go ahead and grab this, and let's think about how these wheels would look. Now, what is the first rule of probability? What is the first rule of probability? All probabilities must be between what and what? The first rule of probability is that every probability, because you can think about Spider-Man, like the probability of seeing Spider-Man. So the first rule of probability is what? So no one talks about probability. That's what it is. First rule of probability is what? Between 0 and 1, exactly. So these can't be probabilities. Like that can't be a probability. What is the second rule of probabilities? That the sum of all probabilities is equal to what? And that's the second rule. There's probably no real order to them. It's just like one rule of probability is probabilities have to be between 0 and 1. So that can't be a probability right there because you can't have negative probabilities or probabilities greater than 1. Both of those are not real probabilities because these are like percentages, or like this would be 180%. So the second rule of probability is the probabilities have to add up to 1. So if you notice right here, the sum of these probabilities is more than 1 because that's 80, that's 110. So you can't have 110%. I didn't make the joke this semester. I was like, when your parents said give 110%, yeah, it's the joke. It's lame if I don't. I gotta get my jokes down. So this one up here looks to probably be valid, probabilities between 0 and 1. And let's think about how these wheels look. So what we should be able to do right here is this first wheel. How does that first wheel look? Well, it's 100% yellow. Does that make sense that this wheel you're looking at here is 100% yellow? Say, Dad, that breaks the laws of probability. I learned that in stats class. He's like, that's all they teach you? You're like, yes, that's all I learned. That's all they taught me. They taught me probabilities have to be between 0 and 1. This wheel right here, don't say that. Don't be nice. Be nice. This wheel right here looks like the following. So right here, can you do a customer organization? Yes, you bet. We'll do that one next, and then we'll do Ella's question because we're on chapter 12. Then we'll hop back. You can. This one right here, we're drawing what these wheels would look like. Does this make sense right here? And then the last wheel, I might not draw it, but how would the last wheel look? Think about the last wheel right here, because this is this wheel. This wheel right here is 40% red and 20%, 20%. So that's the best I can do for drawing a 40%, 20%, 20%. So the last wheel, which is down here, is just going to look how way? I wish I could just reorganize the wheel pretty quickly. It's really easy to draw this one. How does this wheel look? As best as I can draw. You just want to think, can you imagine these wheels? Sure, that's blue. Hey, yellow and blue make green. I mean, I knew that, but it's still cool to see. I'm amused by the smallest of things. Now we actually need green, though. Let's go to a real green right here. It's like it makes exactly that green looks like. Now I've messed up the wheel. So it's an evenly split wheel right there, an evenly split wheel. So when we think about this, the first, the second, and the fourth are actual real wheels that exist. And let's take a look. Since the probabilities, yep, this is possible. There's that first one. And this one's going to be the same thing as possible. We can go to this one is not possible because it adds up to more than 1. Some probabilities is greater than 1 for wheel C right here. And then this one is possible. And then this one has probabilities outside of 0 and 1, so it's not possible. And there it was, not between. There we go. There we go. Great question right there. Good practice on it, and just kind of walking through the steps of it. Just kind of understand the rules of probability right there. Really good question. Can you do an organization estimates? Yeah, let's look at that one. Let's chapter. Yeah, we're on to. Okay. Oh, this is a tricky one. Is it this one or the other one? Because there's two versions, version 1 or version 2. We'll do one of these right now. We could come back and do the other one. Version 1 or version 2. You're welcome, Elizabeth, anytime. Feel free to swing by, ask questions. Version 1 or version 2. One of them works with the first one's more of the addition rule. The second one's more of the multiplication rule. Version 1, this is version 2 right now. Version 1 right here, or version 2. We'll do one of those and we're going to do Ella's question. This one, I think you're talking about this one on the screen right now, right? Version 2, which is currently on the screen. Just confirm, like, yes, you can just type Y or no in the chat. I think we're going to do this one right here, which I'm pretty sure this is the one you're interested in, and then we'll do all this question. Okay, so this one's a little tricky. This one's got a little bit of like, okay, what's going on with it? Let's look right here, and let's take the information, and let's solve it. Okay. So, a consumer organization estimates that over a 1-year period, 15% of cars will need to be repaired once, 8% twice, and 2% will need to be repaired 3 or more times. So let's go ahead and write down these probabilities right here. As first, a car's probability of being repaired 0 times, probability of being repaired 1 time, probability of being repaired 2 times, or probability of being repaired 3 or more times. That's 3 plus. And these probabilities are equal to, and we actually need to use the complement rule right here, 0.02. I am blocking that. 0.02 and 0.08. Yes. Awesome. Now I can zoom in again. 0.02, 0.08, and now we also have, I'm becoming a pro at Microsoft Word. No, I'm not. 0.15, and what is the top probability now? What is the probability a car needs 0 repairs? A car needing 0 repairs has a what % probability, and how did you find that? So this is not asked yet. We're just writing out the problem, putting down our information. So always kind of write down what you know first. I don't know, doing 1,000 problems plus has helped me realize how to solve things. It's like, write down what you know. Exactly, Ella. Great job right there. This is the complement of the other ones. So you know what you can do? You can go right here and put this into 2 sets. So this is the probability of repairs. And the probability a car needs repairs is going to be equal to 25%. And the probability a car needs no repairs does everyone understand what I've done here? I have either your car needs repairs or your car does not need repairs. So either your car needs repairs or does not need repairs. We've divided this into 2 sets right here of the events that your car does not need repairs and the probability your car needs repairs. Green needs repairs. I guess that should be red because it's not a good thing to get repairs. I mean, if you need repairs, you should get repairs. But generally, I don't think of repairing my car as a good thing. It's something you have to do. So we have needs repairs and does not need repairs. These are complements of each other. So either your car needed repairs or your car did not need repairs. The set of events that are in needs repairs are needed 1, 2, or 3 plus repairs. So what's the probability that neither of your cars will need repairs? Now, there's actually 4 things that can occur right here. If you have 2 cars, would you agree with me that one of these things must occur? One of these 4 events must occur. You have 2 cars. So either both your cars will need repairs, car 2 will need repairs, car 1 will need repairs, or what else? What is the other thing that could happen here? Either 2 of your cars needed repairs, the second car needed repairs, the first car needed repairs, or what? This is everything that can occur right here. We've actually just mapped out all the probabilities right here. I wish I'd left myself more room. $5,000 lines of code. Nice. Connor, you should show me this. What up, Connor? Good to see you here. So we have right here, we're working with cars right now, Connor, and we're assuming that the cars are independent to multiply probabilities. So good to see you here, Connor. And you'll have to show me what you're doing with that dashboard because I'm like, oh gosh, I want to see this now. And Connor, we need to talk more about time series because that's going to be really interesting. Only when you're free, though. You're not obligated to help me with designing this course. I just want to make that super clear, unless you be like, Brian, I've lost my job. There's a Seinfeld where Jerry's like, hey, you should go out to lunch. Come on. Like, let's go out to lunch. And the guy's like, well, I got a big meeting. And Jerry's like, blow it off. Don't worry about it. And then he loses his job and everything. And Jerry's like, you didn't tell me that the meeting was like important. He said it was a big meeting. So you don't want that to be what happens to us, Connor. You're like, Brian, I didn't have time to do my work, my real work that I get paid to do. So what is the probability right here? Let's do this first. What is the probability that both of your cars need repairs? What is the probability that both your cars need repairs? So I've got everything listed out here. It's a little small to read. You don't need to read the top text. You just need to look at what I have right here. The probability that your first car needs repairs and your second car needs repairs is what? So the probability that your first car needs repairs and your second car needs repairs, which we're assuming they're independent right here, which is a mighty assumption that your car's breaking down or not dependent on your other cars breaking down. A little bit of a, is it really independent? Is it really? I think you're right, Ella. I think, did I just say not need repairs? If you're doing not needs repairs, I think that's correct. So the first does not need repairs and the second does not need repairs is this right here. And so 0.5625. And the probability that they both need repairs, which I think is the first question it's asking, is going to be, so that's 1/16th, so that should be 0.0625, because it's 1/16th. Does this make sense right here as we draw this out, that your first car needed repairs and your second car needed repairs, probability of first car and second car needing repairs multiplying together, and we get this probability right here, which is the probability that both of your cars needed repairs. This is the probability that neither of your cars needed repairs, and I could actually solve for you mathematically because I know these have to be equal, and there's two events left, so we could take 1 minus, there's multiple ways to solve this, or it's just going to be 18.375. My brain's breaking. Sounds about right. 18.75. So this right here is actually the probability of the first car not needing repairs or needing repairs and the second car needing repairs. And this is equal to, I can't really use both colors for that. And we've actually listed out everything that can occur now. And this one has the same probability of that one. What do all these probabilities add up to here, Ella? What does every one of these probabilities add up to right here if we add them all up? We've listed out everything that can occur. And that's how I actually solved for it, because I can just multiply those together and get the answer anyways. So I could do this right here, and that's going to be that answer right there. So all of those add up to what? They add up to 1. And then I knew that these two were the same mathematical, because there's a rule of multiplication that doesn't matter which order you multiply things in. It's the same thing, like 2 times 4 is the same as 4 times 2. It's just a rule. I don't know what the name is. Names don't matter. Yep, so Clarissa, we actually have all the answers on the screen right now. We're going to use this to help out. This diagram right here, I'm going to vanish. But this diagram on the screen that we've created shows us all the answers, and we got a lot more practice by doing it. So let's go over here to the answers, then we're going to do Ella's question. So this question says, neither car will need repair. So if neither car needs repair, that is this scenario right here, 0.5625. So neither car needing repairs is 0.5625. Both cars will need repairs. Well, we just did that one on the very bottom right there. Both cars needing repairs is this one, 0.0625 right there. And so both cars will need repairs. And then the last one gets a little bit confusing right here. The probability that at least one car will need repairs. At least one car will need repairs. So what is the probability that at least one car will need repairs? So at least one car will need repairs is what? So what is the probability that at least one car will need repairs? What is the probability that at least one car will need repairs? So what is the probability that at least one car, it's going to blank that whole thing out. What is the probability, you can't see if I do that. What is the probability that at least one car will need repairs? Sure, that's fine. Few ways, there's multiple ways to find this exactly, Ellie, you're on the right track right there. You could add together these probabilities here, but it's just, you can do 1 minus because either neither of your cars need repairs or at least one car needs repairs. We've set up a complement right here. We could just add these because these are disjoint events. So the answer that Ella has on the screen right there is the same as just adding together these probabilities, or we could subtract this from 1 because the sum of these is equal to 1. So I'm going to do it the way Ella's doing it right there. It's just much quicker to subtract from 1. Sure. We might have just lost the problem. Oh, okay, we didn't lose it. 1 minus 0.5625, and that's the probability of at least one needing repairs, and we've done it. We've done it. Ella, which was your question again, Ella? Let's hop up to chapter 13. Reappear on the screen. Chapter 13, one of the difficult chapters. Chapter 13 is one of those chapters where people just say, Brian, this chapter got way more difficult. How do we do this? Is it the homework or the quiz, Ella? Is it this one? I think you mentioned something like this. If you can remind me, the histogram one right here. I think it is this one, right? So, yes. Ooh, this one's going to be tricky. Did they change this? Did they change this semester? Ooh. Okay. There's a small chance I could get my first... Oh, it's the quiz one? Let's do the quiz version. There's a small chance Brian could make an error. Let's find out if Brian gets it right today. I know the central limit theorem, but there is subjectivity to an answer sometimes. So let's see here if Brian gets it right. It'd be good if I got it right. Okay, here we go. Very similar question. It might be the same question. Yeah, it's the same question. They might have changed this one also because I swear it looks better. It's working better at 200. So, oh, yeah. Look at this. Yeah, if they're not... Okay. This is a great question now. If the answer is what I think it is. If the answer is not, I'll be very mad. So, as the sample size increases, the center of the histogram will not move. So the center of the histogram does not move because, and let's show here mathematically, because where is the center of the histogram at when we do the sampling distribution of the sample proportion? So as the sample size increases, the center of the histogram will do what? Because there's the center of the histogram, it's at P. So if we increase the sample size, what happens to that? The center of the distribution, right there, that's mu, or the mean of the distribution, which is P right now. So we're saying we expect for it to be P, and we can see right here, there's the center of the distribution, which is the mean of the distribution. So what happens to this if we increase the sample size? Like what happens to, let me highlight it. What happens to that number right there? Yeah, nothing. It stays the same. And we're doing a simulation, so the simulation might show small differences, but that's just due to random chance. So it stays approximately the same, but theoretically it should stay identically the same, but randomness will create differences. The shape of the distribution is going to do what? So the shape of the distribution, and this is very, very, very important, the shape of the distribution as the sample size increases, and this is the central limit theorem, will become more what? Something we need to understand that the central limit theorem says is that it's going to become more normal as the sample size increases. For larger samples, we're going to see that it becomes more normal. Yep, so it's going to become more normal. So it's going to become more normal. And we can see this. Here, I'm going to show an example of it. I don't have that up currently. Give me 2 seconds. I'll show you a visualization of it. So let's go here to the binomial applet, and it's similar-esque. So let's go here to the following. Okay, here's a sample of 10, 50, 500, which it breaks it. Great. 100. As the sample size increases, the distribution starts to look more and more what, Ella? And this is the key right here in what we're covering. As we increase the sample size here, you can see it kind of very quickly in this, that as the sample size goes from a very tiny sample to a larger and larger, and as Ella is saying in the chat, it's becoming more normal. So you could view this especially if you went something from like 1, or let's go here to 10, to 20, to 30, to 40, to 50, to 60, to 70, 80, and it starts to become more and more normal, and we break the applet. I don't know why his applet breaks on that. So it becomes more normal as the sample size increases. And we also see this in the simulation where it's not normal, more normal, and very normal. Sample proportion and the variability in the sample proportion does what? Now, variability is just a measure of standard deviation. So when it comes to variability, what happens as we increase the sample size right here, which is the spread? The sample size will do what to the standard deviation? If the sample size goes from something like 5 to 50 to 500 to 5,000, what's going to happen here to the standard deviation as we have an increase in sample size? The standard deviation, because we're dividing by n, and then we're square rooting, but mostly the important part is the dividing by n. So as we go from a sample size of like 5, yep, it's going to get smaller because we're dividing by the number. So it's going to decrease the variability. So the variability is going to decrease. These do demonstrate this because simulations demonstrate the truth. Is that it? Yeah, sure. I thought there was more to that. Oh, man. I thought there was an additional question. Maybe they removed it. There is one on one chapter that has like an additional thing. It's an open floor right now. We just got that question done. We've done a few of these today, but let me know which question you're working on, which one you're thinking about. I am out of coffee. I'm out of coffee. I'm out of orange juice. Last drop of orange juice is done. No more orange juice, no more coffee. Sad, sad world. Let's play our happy sad song while we're here. If no one has questions, investment website, of course. Yes. We got the music playing. You know, I don't know. Every time I hear the song, I think about Josiah. I need to buy a piano. Such a beautiful song. What would the managers... Okay, here we go. An investment website can tell what devices are used to access their site. Yeah, we can do it with Google AdWords. That makes sense. The site managers wonder whether they should enhance the facilities for trading via smartphones, so they want to estimate the proportion of users who access the site that way. They draw a random sample of 129 investors from their customers. Suppose that the true proportion of smartphone users is 38%. Okay, so what have they just given us? What have they just given us? This is very important, and we need to know. What have they just given us right here? What have I done? Sure. So two numbers, suppose the true proportion, and that's so key right here. That is majorly important. Sure. No wonder I had it so small. What in the world? I do not understand. This thing is possessed. I'm going to like reinstall Microsoft Word this weekend. Yep, that's P. There we go. So what else would you find right now as soon as you have P? Instantaneously, I'm going to find this. Like if I have P, so we know P is equal to 3.8 or 0.38. And that's the weirdest 3 I've ever seen. And Q. So as soon as you have P, you find Q, like, okay, cool, we got it. Now, what would you find down here if you know this? Because if you know what kind of problem this is, you'd be like, well, wait a minute. We're just going to talk about normally distributed with a mean of P and a standard deviation of P times Q over N. Brian, better handwriting. P times Q over N square root. And we're just going to plug in the numbers right here. We're going to make our pen smaller so we can actually write legibly. Please work. There we go. Oh, whoa, 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 whoa. That's Q. Go away, Q. 0.38, 0.38, 0.62, and 129. There we go right there. We are good to go. We got all the information we need. P times Q over N square root. Let's find that. P times Q over N and its quantity square root. P times Q over N square root. There we go. And we know the mean of the distribution. Mr. David M. Lane, if you're watching the chat right now, here is the David M. Lane website. Thank you, Mewbot. He's going to put it in the chat there for us. P times Q over N square root. P is 0.38. There's Q. Sure. Must be similar to what we had before. Here's the distribution we are getting. The distribution is showing us what is possible when we go out and take it. There is a third standard deviation. Sometimes his website doesn't post it. I think we might have had some stuff on the conditions here. What would the manager expect the shape of the distribution to be? If we meet all the conditions, it's going to be unimodal and symmetric, which means normal. What would the mean of the distribution be? That is the P we found, because the center of the distribution is equal to the mean. We put that right here. And this is also shown in the notes right here. So this is the mean of the distribution right here. And we also have it in the notes. There's our fun example from class. We also have it in the notes right here that the mean of the distribution for the sample proportion is P. Lots of practice right here. This is a very kind of knowing how to do the math type chapter. The standard deviation is what we just found. And let's go ahead and put the standard deviation in here. We paste that and we go down to 3 decimals. There we go. And is that it? Hey, there we go. So for the first part, it doesn't meet the conditions. How do we figure that out? Oh, so what are the 3 conditions here, Ella? Let's review the 3 conditions. So practice of 3 conditions right here. Condition 1 is what? So we always have condition 1 is what? Condition 1. Everyone's about to hear it. We always know condition 1 is what? If you don't meet the conditions, you can't use the normal curve. So if you were to fail the conditions, you'd be like, we can't use the normal curve. Condition 1 is that we randomly sample. Condition 1 is always that we randomly sample. We try to make that very clear in the questions we write. So did Brian randomly roll the dice right here? Random, 10%, and then we always pause. Don't worry, you are 100% right here. And then success, failure. And I went one further in class today at the very end. We had already finished. Sometimes I never do material that you wouldn't hear if you weren't in class. But maybe I have to grab that photo. Where did I put it? Did I close it out? After class today, I talked a little bit about, let me go grab it off of Discord because I put it in Discord. So I'm going to go grab this photo. I did the conditions today. And here are the conditions for pretty much the whole rest of the semester. So let's drop this here. Let me reappear. And here are the conditions for the rest of the semester right here. You'll always pause after the second condition. We're currently doing success failure. If it's quantitative, it'll be nearly normal or large enough n. If there's 2 variables and it's quantitative, you'll do independent means. And if we're doing the chi-square test of independence, it'll be expected cell count. And if it's chi-square test of independence, it'll be count data. So this is why I always say random, less than 10%. And these are the conditions right here. So this is another great screenshot to have if you don't have it. But this is pretty much the conditions for the rest of the semester. Does that help out with this here, Ella? You'll always remember random, randomly sample, then less than 10% is sampled of the population. Success failure is we need at least 10 successes and at least 10 failures. We can actually check that for this question that we just did, which we didn't do, but we could check. 129 investors. So that is the sample size. So we do 129 times 0.38. That's greater than 10. So that's NP right there. That's greater than 10. And then we go 129 times 0.62, and that's NQ right there. So both NP and NQ were greater than or equal to 10, which means we passed the success failure condition. Does that make sense here, Ella, for this question, how we have at least 10 successes and at least 10 failures via NP greater than or equal to 10, NQ greater than or equal to 10? This question didn't have us check that, but actually it kind of did by saying it'll be this shape. If we meet all the conditions, it will be unimodal and symmetric. If we don't meet the conditions, it won't be unimodal, symmetric, normal. So it's kind of alluding to it. It's like, did say, well, the manners, yeah. If you meet the conditions, it'll be normally distributed. But good stuff right there. What additional questions are there? We've done a good bit of these today. Let's see how. We did this one another time, but feel free to ask questions. I guess we have, is it probabilities due tonight? All that good stuff. Someone posted something on the Discord. Is that me? Connor says, dear. I feel like if Connor's still watching, Connor could always appear. I could go into a Discord call with Connor and have him give advice to students. Awesome, Ella. Connor, if you're still here. messaging Connor on Discord right now. So, because we're at a lull right now, I'm going to hop to space. We'll see. Go to just our normal music here. Anytime you have questions, feel free to swing by. Busy week. Yeah, no, that's something. No, HDT, you're totally right. I need to. Nick said he would talk. Nick's been pretty busy. And I'm trying to think who we have who's a Milton Scholar. I got a hold of Nick, and he said he could do an interview. We need to set up in the future. Was Mark a Milton Scholar? Already counted it once. I'm trying to think who else I have on call. Don't want to put him on the spot again, but that's a great question, HG. Yeah, could you help me with the dresser from chapter 12? Of course, Cooper. Thank you for swinging by, Cooper. Let's get that question up and going. Let's go to chapter 12, especially right now during this period right now. Perfect time to ask questions because I'm just like trying to figure out what to do. Trying to fill the time with something to work on. And great time to say, hey, can you work on this problem? Yes, of course. Let's hop back here to the main screen. Let's do this right here on the main screen. The dresser problem. Here we go. In a dresser, there are 9 blue shirts, 5 red shirts, and 2 black shirts. So let's go ahead and take the problem right here. And with this problem, we're just going to listen to chill music. Might do that for the rest of the stream. Perfect chill stream. And here we are. So we have a total of 16 shirts, I believe. I would have more questions if I started the assignment earlier. Start early. Start early. That's me talking to myself also. So we got probability of blue shirt. So blue is going to be 9 out of 16. Probability of red is 5 out of 16. Probability of black is 2 out of 16. Horrible handwriting, but we can read it. So we have all the probabilities right here. 5 out of 16, 9 out of 16, and 2 out of 16. Sure. What is the probability that a randomly selected shirt is red? Should be 5 out of 16, so we can just divide that here. That should be 31.25. 31.25. What's the probability it's not black? So let's go back here to the question. There's that one. And the probability of not black, well, the probability it's black is 2 out of 16, so 14 out of 16, which is 7/8. 7/8 mathematically is going to be 87 oh, no, my brain not working. 87.5. Did I do it correctly? We got to do it by the end of the song. Yes, we did it. And so that was 14 divided by 16. So it's the complement. Either shirt is, but I haven't processed the whole thing yet. That's all right. We did some help stream on it earlier today. And yes. So this right here is the set of not black shirts. Sounds like a Borat joke, not black. So either the shirt is black or it is not black. And the set of not black shirts is 14 out of 16. I'm probably blocking that, aren't I? No, not yet. And the set of black shirts right here are 2 out of 16. So either the shirt is black or it is not black. Does that make sense, Cooper? My shirt today is blue. I had the higher probability of 9 out of 16, but you can also separate this into other things like the shirt is black or not black and create this dichotomous relationship where you have complements. So it's important to know that a complement is either something happens or does not happen. So we've created either the shirt is black or it is not black. And the set of not black shirts are the shirts that are blue or red. And so you could add these. You could just simply add these. 9 plus 5 is 14. Or you could subtract from the total. Ask more questions. We'll put on some music right here. We'll hop back to space, but this is your time. If you have questions, let me know. My hair is just everywhere. Time to ask questions is now. We got a review for the test. You know what I might try to do? I gotta get that epic speed runs here for the channel. So we can watch, so I can be like, let's do a speed run. Because I would totally do that right now. Should I speedrun a chapter? Is that what I should do? If you're here, maybe I could do that for the end of the class right now. Let me go to the Stretch 1 website. Speedrun a chapter. If no one else has questions, I might do that. But if you have a question, let me know. It's always your chance to ask questions. Review material for exam 2. Topics. Here we go. I now have the topics. I have the topics, and we can go over the topics. Okay. Randomness is so short. Okay. Let's see right here. We'll see what people are saying in the chat. I think we might do it. I think we're going to try a speed run. Get ready here. Let's see if we can get one speed run out of the way for this. About to do an epic speed run. Getting hype. Getting prepared. Not repaired, but prepared. So let's get ready here. I need to get the screen situated. You have to do a certain screen situation for epic speedruns. Okay. Let's head over to that epic speedrun screen. Let's do this. Okay. Speedrun. Let's got this open. We need to be over here. You know what we might do? We might just take this and screenshot it. Speedrun timer's up. And I need to put in, there we go right here. And I don't have these all. I spent a lot of time putting in the videos, but I'll timestamp it because I spent a lot of times typing into this. So you know what we're going to do? We're going to use this right here as the epic speed run. I'll make sure everything looks good right here. Less pressure since I don't have to do 10 takes of this. I'd do oh my gosh, it's so many takes. This is epic speedruns live. We're going to see what happens. This is like 1 attempt speedruns. Got 22 minutes left of office hours. We're going to do an epic speedruns of decision trees. This is epic speedruns live, everybody. Let's do this. Speedrun of decision trees. Let's begin now. Oh, wait. Begin! That's what it does, so we don't do that. When it comes to decision trees are something that take a bunch of x variables, a whole bunch of x variables, and look at one y variable. So let's make sure we understand this, that we're looking at one y variable. That means on our tree over here, we have one y variable of interest, and then we have a whole ton of x variables. You'll often see this down here on the bottom, that your tree is splitting up on multiple x variables. Now, the x variables that can go into our tree are going to be things that are either quantitative or categorical. Either which way is fine, and the same works for your y variables. Both your x and your y variables can be quantitative or categorical variables. It's fine either way, but there are variables that we do not want to include in our tree. The variables we do not want to include in our tree are going to be identifiers or things that act like identifiers. And what do we mean by things that act like identifiers? Something that acts like an identifier is going to be a categorical variable with tons of levels. Like one of my favorite questions, what is your favorite ice cream flavor? And I'd probably say everything but the kitchen sink or cookie dough. And there's so many levels to this. Think about it. Levels is an answer to a categorical question. So what state were you born in? Could have up to 51 levels or 50 levels. I got to figure out how many states there are. So with this, we would have lots of levels. Or you could say, that does not apply to me. I was not born in a state. So there are more levels to the variable than we even considered. And with this right here, if the variable has too many levels, it can act like an identifier. Now, identifiers are things that are unique for each and every observation. A categorical variable with many levels might act like an identifier, but is not truly an identifier. Next, we need to understand what partitioning the data means. And partitioning the data looks like the following. We take our data, and it's in one big clump. Basically, you have everybody up here all together, maybe 800 observations. And then you're going to take and section people off into different groups. Now, this is done via the x variables here, and they're not always equally split. Sometimes you might have 650 people in this group, and maybe 150 people in this group over here. You know what we're going to do? we're going to go right over here and look at a decision tree. So let's go ahead and grab a decision tree, and let's go into decision trees now. We're pulling up the decision tree here, and let's take a look at a decision tree with some data. Here is our decision tree data, and let's go ahead and make a decision tree and start sectioning apart the data. Analyze, partition, and let's go here to predictive model, partition. It's off the screen a little bit, so I'll let you see. So we're going to go here to analyze, predictive model, and partition, which is going to bring up the decision tree interface. Now, one thing I want to point out right here is we will use as many X variables as we can, but we will not use things like identifiers. So we don't want to use this one right here. Also, major is going to be a variable with too many levels, and it's not quite an identifier, but it'll act like one. So once again, we do not use things that are identifiers or act like identifiers, but we could predict something like, let's say if you were born in Tennessee. I'm just going to take a whole bunch of X variables here, but I'm not going to take major. I'm just going to drop these over here, and I'm going to take more X variables, and I'm also not going to take somebody's favorite phone app, because that'll also act like an identifier. And let's just put all of these X variables in right here, and let's look at the decision tree. Now, in this decision tree, we are predicting a categorical Y variable. We know this because we can color the points because we have people here who are born in Tennessee and people who are not born in Tennessee. And when we split the tree right here, notice how when we split the tree, it'll split them into groups like we were just looking at a moment ago. So we can see right here, depending on this variable right here, we have people's views on life on Earth. We have people who are more likely to be born in Tennessee or people who are less likely to be born in Tennessee. We can split on any variable we want, like we could split specific right here just to see what happens if we choose a specific variable. So we don't usually force a tree to make a split, but let's go to a variable like, are you in the honors program? And with this right here, there's really not much of a difference. If you look at this, the R squared is actually horrible right here. We have an R squared of 0, opposed to the previous split where we actually got an R squared of 3%. Still not that much of the variation explained. I'm trying to make sure the whole tree is shown on the screen. But if you notice, we started up here with 1,905 people, and we split them into 2 groups. It doesn't have to split evenly, but it's splitting on this variable and separating people out depending on their views. So this is what we have right here. We are partitioning into splits and into different groups. When do we stop splitting the tree? Now, this is a big question right here. We stop splitting the tree usually when we see smaller increases in R squared or the splits become illogical. Now, what do I mean by a smaller split in R squared? This is where we're looking at the split history. So the split history right here, the split history is going to show us the history of the R squared. So as we make more and more splits right here, as we go into more and more groups of people, like this 150 might be split apart into other groups on another X variable, maybe 100 go over here and 50 go over here, what we would notice is we would notice that the R squared would go up each time. We'd start with an R squared of 0, and then maybe the R squared goes up to like 10%, and usually it gets smaller as it goes up each time. So here's after the first split, which is right here. But once we get to another split, down here at the bottom, we would have two splits, and the 2 splits are as follows right here. Let's highlight this in blue. This is the 2 splits, split 1, split 2 right there. So you're at your second split, and then we would look at, sorry, it's changing pens on me. We'd look at the increase in R squared right here. So if you notice, the R squared is going up, and it generally goes up less and less. So after each split, it's important to note that your R squared will increase. Your R squared will increase after each split, and we generally decide to stop splitting the tree as we see smaller and smaller increases in the R squared. And where do we see those increases in the R squared? In the split history, which is going to show us after each split how much the R squared is increasing. When we interpret the tree, we need to know how to interpret the R squared. So if this tree right here was trying to predict something like, let's say it's predicting born in Tennessee, whether people born in Tennessee, were you born in Tennessee? That's what this tree is predicting right here. The R squared is going to be the following. Let's take a look at an interpretation for the R squared. We need to remember that it is blank percent of the variation in Y is explained by the variables in the tree. So blank percent of the variation y is explained by the variables in the tree, and we plug into here the r squared. So let's make an example right here. Blank percent of the variation y is explained by the variables in the tree, and let me go ahead and get a decision tree that looks halfway decent for us on the screen. This tree right here only explains 3% of the variation, or 2.9 to be exact, and that's the r squared. 2.9% of the variation in whether or not people are born in Tennessee is explained by the variables in the tree. And that's not much variation at all. Very, very, very little of the variation. We'll make one more decision tree right here. Let's go to Analyze, Predictive Model, Partitioning, and let's predict whether or not someone's in the honors program. We're just going to grab a whole bunch of X variables right here. We're going to remove favorite phone app. And so let's put all those in there. We don't want to put honors program because we're using that. And we're going to remove major. And let's put these right here. And here we are. We can actually remove the color on the points. And let's go to rows and clear row states because this is a quantitative. Oh, we are predicting honors program. So we should recolor the points here. So you can see the honors students are up here and the non-honors students are down here. I'm going to go away from the speedrun screen for a second. We'll be right back to it. But I need the full screen to show this. And let's split the tree. As we would expect, the honors students are the students with the higher GPAs. So this one's making a lot more sense, and we're getting a much better R squared. And you can see right here, students who are in the honors program are students basically with really high GPAs. Let's go ahead and look at the leave report right now, which is our last thing to understand. We have 4 leaves. And one thing I want to point out right here, and this is so very important, is the following. When you are looking at this leave report, I always want you to think about it this way. In your leaf report, you will have here leaf 1, leaf 2, leaf 3, and leaf 4. And these leaves go down the following: 1, 2, 3, 4, 1, 2, 3, 4. Right over here, we have the distribution of the y variable, which is what you're seeing right here. This is all the distribution of the y. It is I'm going to highlight here in a second what it is, but it is this right here is the distribution of the y. That's the distribution of the y variable, which is also shown to you right in here. That's the distribution of the y variable. Over here, you have the x variables that are the splits. These are the x variables it's splitting on, which is like GPA. That might look like I'm highlighting GPA there, but I'm just trying to highlight this. So GPA, the top portion right there, is what we are splitting on, and that's the variable we are splitting on, and the y is the distribution right there that looks like a bar graph. So very, very important, we're looking at the distribution of the y variable, and then these are the x variables right here that we're splitting on. So those are the x's we're talking about. Very important to understand to know what's going on with this output right here. Now, if you look at where the majority of the honors students are at, let's zoom in on this output here a little bit, and we can see the largest proportion of honors students are in leaf 1, and these are students who have the following characteristic. They have a GPA greater than or equal to 3.84, and they have a GPA greater than or equal to 4.32. So these are the really high GPA students, and it makes sense that the majority of them are honors. The students who are least likely to be in the honors program, only about 1%, 1.19%, and there's 1,016 of them. You can also see down here, there's 12 students who are in the honors program, 1,004 who are not. And you'll notice right here that these students have the characteristic that they have a GPA less than 3.84. And then this is also the bar graph of the following distribution right here, because this is leaf 4. So it's very important to be able to connect this data together and understand where your y variables are at and where your x variables are at. These are the x variables right here, which are the blue highlighted portion. So hopefully the color coding here helps you a little bit and helps understand what is going on. This is a categorical tree right here where we're looking at the different groups. Now, one last difficult question, which I'll leave you with right here to end off, and we'll remove out our little help guide, is what proportion of students who have above a 3 or a 3.84 or greater were in the honors program? So here's a tough question to end. Let's put the question on the top of the screen at the end of this speedrun right here. What proportion of students who have above a 3.84 were in the honors program? What proportion of students who have above a 3.84 were in the honors program? So if you're looking at this, you're actually considering all of these students right in here. These are students who have above a 3.84 here, here, here. And if you look, it's actually this group right here. This is where people usually get stuck and they say, how can I find an answer to this group all the way up here when I'm giving the information down below? But I'd like you to think about this for a moment here and think, wait a minute, this is group 1, group 2, and group 3 all go back into this group. They're all a derivative of this group. So going down to the data down below, we can look at group 1, group 2, and group 3. Group 1, group 2, group 3. Well, we see here these are the students in the honors program in those groups, which represent 27 students right here. That's 27 students. So let's make a little annotation of that. That's 27 students. And as follows, we'd have the other students, 49 students right there, and 35 students right there. It looks more because there's less students. There's only 123 in that group. So what would we do right here? We would add together these numbers, and we'd get 35 plus 49 plus 27, 111. And let's go back up here, 111 out of this amount right here. So 889, or 111, divided by 889, and there we go, 12.48. And let's go back to the screen here, and let's hop back to the speedrun screen. Let's go back to speedruns here. Let's do it. Oh no, it restarted timer. We can't have the other timer on the screen. That's got it right here. We'll bring up the actual notes so it looks a little bit better. But we've covered all the topics right now. Understanding how to make decision trees, how to read decision trees, how to read the leaf report is very, very important to understanding the theory behind decision trees. And with that, our speed run is over. Whole decision tree is done in just over 14 minutes. We haven't had someone challenged to a speed run in a long time. Easyscape, this is to you, man. Time for you to do a speed run. Just got to make it happen, man. Statistics speed runs is where it's at. There we go. There are decision trees. I need to cut this from the video. I'll probably throw an ad on this, but no, like not on this video, but I throw ads on the other ones if anyone wants to learn decision trees. Because we get views every once in a while from people outside of UT, which I really like. And then we can use that money for Kahoot giveaways. Yay! Kahoot giveaways. Let's hop back to space. Where's my music for space? Space music. Try to do a few more speed runs during class. I can cut these out then, or not class, but during office hours. So maybe Thursday we'll do some speed runs too, but then I can cut these out. Cut it out. I'm probably older than Dave Coulier was. Dave Coulier. Coulier. I don't know how to spell Dave Coulier. Dave Coulier. Is that how he spells it? There he is. Oh, I'm way older. Man, that's a bummer. $1995. This is Brian feeling old and aging. Tonight I plan on charging through the code. Not awesome work, HGT. Whenever you get stuck, let me know. Brian's just reminiscing about being old. I mean, like, man, I remember the 90s. Yes, HGT. Anytime you have questions, let me know. That's what we're here to do. We're here to help, answer questions, work on stuff. Play music. We haven't played this one in a while. I think that's got it. We did a speed run. We can cut that out. Post that for people to see to help out. I was like, oh, it's last semester I did like 4 or 5 takes of speed runs. I definitely like, oh man. I'd finish teaching some nights around like 5 or 6, and then I'd be doing like takes of speed runs till like 10 p.m. Then I'd be editing it till like 1 a.m. And I was just like, I can't do that again because I was just like, I was exhausted. I was just like, and then I've mentioned it before. My body was like, no, you can't do that, Brian. You can't work all day and stay up all night and then wake up and do it again, and do it again, do it again, do it again. Your body just like, no. You need to make better plans. You need to organize. You need to figure out strategy. to make it all work. Is that what we do? So if we get a lull, we can do a speedrun during this and then cut it out, and then we can put it there and we can have a speedrun. I like it. I like it. I think these are like for headphones or something. But that's got it. HDT, excellent work. Swing by office hours anytime, anybody. If you're ever here and I'm doing something, ask questions. Great work today. We got a lot of 201 in here. We'll head off. But your brain will evolve into a coffee bean. Yeah, pretty much. I mean, that's all I have. Got a ton of coffee right here. Second cup of coffee down for today. Mario mug, priceless. Some piano music. But it's all about starting early. Like, I don't know. I had a great winter break. I had a really great winter break. Got to like just play video games. We got Hades, and Hades is so good. Hades is a great game. I had a friend tell me that. Guy who lived in my apartment complex. Really nice guy. He's like, you should try Hades. And I was like, yeah. He's like, you like roguelikes. You like Isaac and you like Gungeon. So I was like, yeah, I should check that out. And I didn't. And then I didn't. Yeah. Finally did. He was right. That's got it. We'll put on our usual end music here. With that, everybody, we'll head off here. It is end of stream time, but I will be back teaching statistics later today. BAS 320. I will see you later. If you're not in the class, don't worry. I will see you soon. Bye for now, everyone. Bye.